In 1942, she was a 23-year-old graduate student in physics, working at the University of Chicago and working alone. She was finishing up her dissertation in an empty program. Once the department had been teeming with students, but now with the United States at war, almost all of her colleagues had left to enter into various projects devoted to developing technologies that would give Allied soldiers and sailors an edge on the battlefields and oceans of the conflict. Each day at 5 p.m., she would leave the university to swim in Lake Michigan, and soon found that she had a companion in her afternoon ritual. Herbert Anderson also swam at that time, and soon the two became acquainted. Anderson was the colleague of Enrico Fermi, and through his contact, Leona Woods soon found herself working with a team of researchers that she didn't know had been brought together on a project that she could discuss with no one. She had a certain expertise working with vacuum tube technology, and soon found herself building Geiger counters for a project being put together in the very squash courts where she had played the game as an undergraduate. She constructed a very specific type of counter, optimized to detect neutrons with an energy and determination that stood out to the entire team there. Laura Fermi remembered Woods as, quote, a tall, young girl built like an athlete who could do a man's job and do it well. She was the only woman physicist in Enrico's group. At that time, her mother, who was also endowed with inexhaustible energy, was running a small farm near Chicago almost by herself. To relieve Mrs. Woods of some of the work, Leona divided her time between atoms and potatoes. Unquote. On December 2nd, she joined her colleagues who had built the first nuclear pile and oversaw the operation and readings of all the important detectors that would tell the team whether they had achieved the goal of creating a self-sustaining nuclear reaction and warn them if that reaction was growing too quickly and posed a danger. If her detectors detected a surge in the number of neutrons being emitted by the pile, they were supposed to trigger a safety mechanism that would shut down the reaction. The problem was, no one had ever done this before. Once started, did anyone really know if the reaction could be shut down? She was the only woman present at the fateful time of 3:25 p.m. when the reactor went critical, turning to Fermi after the announcement to ask, when do we become scared? The truth was, everyone was already working scared. Asked many years after the war what the attitude of the reactor team was, she responded, quote, I think everyone was terrified that we were wrong in our way of developing the bomb, and that the Germans were ahead of us. That was a persistent and ever-present fear, fed, of course, by the fact that our leaders knew those people in Germany. They went to school with them. Our leaders were terrified, and that terror fed to us. If the Germans have got it before we did, I don't know what would have happened to the world. Something different. Germany led the field of physics, in every respect, at the time the war set in, when Hitler lowered the boom. It was a very frightening time. Unquote.
Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery.
Series 2, A History of the Atom. Episode 20.2, Supplemental. Enrico Fermi, the Pope in America. When Fermi arrived in New York and formally accepted the employment offer from Columbia, he was still unaware of the work of Hahn and Strassmann at the Kaiser Wilhelm Institute in Berlin. That news would arrive just a few weeks later with Niels Bohr, who would be spending a sabbatical at Princeton to work with Einstein at the Institute of Advanced Study there. For Bohr, there were really only two things on his mind at this point: nuclear fission and the increasing prospects of a second Europe-wide war in his lifetime. While he initially only brought with him the specific results from Hahn, it was just a few days later that he received a telegram reporting the success of Meitner and Frisch in explaining and testing for nuclear fission. Now, before we move forward in the narrative, there are a couple of things, I think, that need to be said here. First, while the standard histories of this series of development often present this as the defining point in the development of fission, it should be understood that it wasn't necessarily seen as such at the time. While Meitner's explanation and Frisch's experimental confirmation were vitally important, they really only convinced the nuclear physicists and chemistry research community that fission was in fact taking place. With their announcement, there was still a lot of work to do. To begin with, their results had to be confirmed by other groups of researchers. On top of this, there was a real need to more fully understand what was actually taking place in the process. Meitner's work was based on Bohr's semi-empirical liquid drop or compound model of the atom, but it should be understood that the model was just an approximation of what was going on. It gave the physicists a way of approaching the problem and in doing some calculation, but it wasn't detailed enough to accurately predict everything that was taking place. To gain that level of understanding of the fission process, a lot of data would have to be gathered and analyzed. The second thing that needs to be pointed out is Fermi's reaction to the news, as I think it's really illustrative of how a good scientist thinks about the work they're doing. Laura Fermi relates a conversation she and Enrico had regarding the news that Bohr relayed to the physics community in the United States on and shortly after his arrival, and I'd like to sort of share it with you here. And this is taken directly from her book, Atoms and the Family. So we're going to start with a conversation between Laura and Enrico in her voice to begin with. Quote, Enrico tried to explain fission to me. He does not like to talk shop at home, except when extraordinary events grant a breach in the rules, and the recent discovery well deserved the exceptional treatment. I am a slow thinker and the lack of necessary background to grasp scientific matters easily. Wait a moment, I said. Let me see if I follow you. Hahn bombarded uranium atoms with slow neutrons. That's right, he said. And broke some of them into two big chunks. Still correct. And uranium atoms would behave in the same way for anyone. What do you mean now? I mean that every time uranium is bombarded with slow neutrons, at least part of it would break into two halves. That's right again. But then, in Rome, you and your friends also bombarded uranium with slow neutrons. Then if uranium behaves always in the same manner, you must have produced fission without recognizing it. That's exactly what happened. We did not have enough imagination to think that a different process of disintegration might occur in uranium than in any other element, and we tried to identify the radioactive products with elements close to uranium on the periodic table of elements. Moreover, we did not know enough chemistry to separate the products of the uranium disintegration from one another, and we believed we had about 4 of them, while actually their number was closer to 50. But then, what has become of your element 93? What at the time we thought might be element 93 has proved to be a mixture of disintegration products. We had suspected it for a long time. Now we are sure of it. Then I thought to myself, fission is the death warrant of your element 93. To Enrico, however, the discovery of fission had a deeper meaning than proving that an interpretation of experimental facts had been wrong. Foreseeing important developments, he set himself to work on the theory of the phenomenon. Unquote. Now, Fermi really could have been upset by the overturning of the work in his Nobel Prize of just a month earlier. He could have dug in his heels and said that he was still correct, as the other scientists had done with their work in other cases that had been overturned at a later date. Instead, he saw the role of scientific investigation as being to uncover the fundamental relationships that govern matter, and his work being to undertake that investigative process to the best of his ability. So what if his interpretation of the data gathered had been wrong? There was better data now, and he wanted to understand it better so that he could better describe nature. I think this is the sign of a scientist whose work is not tied up in his ego. Fermi knew he was a good scientist and he had done tremendously good work. All of the research being done rested on his discovery of slow neutron bombardment, something for which he would have received the Nobel Prize even if he hadn't claimed to have found element 93. For him, it was the discovery that was important rather than the recognition, and now, with this new information, there was a lot more to discover and to understand. So upon hearing Bohr's news, Fermi shifted into what I like to think of as theory mode, and he began working out what the data would mean in terms of the theory. While Meitner and Frisch had posited and then observed that neutrons would be emitted in the fission reaction, Fermi wanted to understand the specifics of what was taking place from a theoretical perspective. His calculations showed that each splitting of a uranium nucleus would produce at least 2 neutrons. If each neutron was absorbed by another uranium nucleus, and then that nucleus were to undergo fission as a result, each would produce 2 more neutrons. This process would lead to a multiplication of fission reactions, each producing energy as a result of the release of the binding energy of the uranium nucleus being split into smaller pieces with less binding energy. 1 fission becomes 2, which leads to 4, that causes 8, and so on. This is what is meant by the chain reaction of Szilard, and Fermi showed that such a thing was, at least in principle, possible for this uranium reaction. However, possible and practical are 2 very different things. The history of science is full of ideas that were counted as possibilities that either never materialized or only did so after an enormous amount of work. The first task would be to determine whether Fermi's theoretical calculations were correct and uranium did give off more than 1 neutron when fission occurred. The next step would be to determine just how large a percentage of these neutrons led to a new splitting of a new uranium nucleus. The work of doing this fell to Fermi and a graduate student, Herbert A. Anderson. Anderson had been corralled by Bohr during a visit Bohr made to Columbia from Princeton not long after he arrived in the United States. Anderson was intrigued by Bohr's news and convinced Fermi to restart his neutron experiments using the new cyclotron Columbia had constructed in the basement of its physics building. This tool was a huge step up from the tabletop experiments Fermi had done in Italy, where his neutron source was an evacuated glass tube that held a powder of beryllium to which radon gas had been added. As the radon had undergone alpha particle decay, the alpha particles interacted with beryllium to knock loose free neutrons. This process produced only a meager number of neutrons by which to bombard samples with. By using the cyclotron as a particle accelerator, Fermi could produce over 100,000 times the neutrons to bombard samples with, and that would allow him to get so much more data. So using the tool, not only was the Columbia team able to verify the results of Meitner and Frisch, but they were also able to show, along with the Jacques-Curies in France, that the samples did emit more neutrons than they absorbed, indicating that Fermi's calculations had been correct. Moreover, working with Bohr, Fermi was able to show that it wasn't actually all of the uranium that was undergoing fission. What the two were able to determine was that the main isotope of uranium, the isotope known as uranium-238 or U-238, did absorb the neutrons, but then it did not undergo fission. It was only the isotope uranium-235 or U-235 and uranium-233 that did this, and only if the neutrons were moving slowly after having been moderated. For future reference, these much more slowly moving neutrons are usually referred to as thermal neutrons. Shortly after this, Fermi and Anderson collaborated with another member of the Columbia faculty, a refugee from the Hungarian brand of fascism, the already mentioned Leo Szilard. The 3 sat down and worked out a design for what was called a nuclear pile. This was a configuration of elements that would allow for a controlled chain reaction of uranium to take place. In the design, it is important to moderate the neutrons emitted from the fission event in order to decrease the chance of being absorbed by the U-238 atoms in a uranium sample, and increase the chance of being absorbed by a U-235 atom in the sample that would cause another fission event. While water was the most obvious choice for such a moderator due to the large amount of hydrogen, it was found that regular water absorbed too many neutrons. There were two other options available. One was what is called heavy water. This is water in which the hydrogen atoms in the water molecules are not the usual single proton in a nucleus variety most commonly found in nature, but the isotope of hydrogen with one proton and one neutron known as deuterium. This had the property of being a good moderator while not absorbing as many neutrons. The downside of this approach was that the heavy water, as it was called, which makes up about 1% of all the naturally occurring fresh water in the world, is very difficult to separate from that regular water. Nevertheless, this would actually be the solution pursued by the German atomic energy projects. Fermi's solution, on the other hand, was to use a completely different material, graphite. He and Szilard developed a design that interspersed blocks of uranium oxide with blocks of graphite. Szilard had obtained about 200 kilograms of uranium oxide from a Canadian mining company that allowed the team to experiment with various designs of materials, a process which led them to determine the superiority of graphite as a moderator at this stage. On March 18, 1939, Fermi reported the results of the research to the U.S. Navy and warned the military, for the first time, about the potential impacts of the technology being developed. As a result, the Navy provided additional resources to purchase graphite and produce blocks of the material to intersperse among the uranium oxide blocks. As the blocks of material were piled up, one layer atop the next, the whole thing was known as a nuclear pile. On August 2nd, the now famous Szilard-Einstein letter was delivered to President Roosevelt, who immediately set up the precursor to what would be known as the S-1 Uranium Committee, to oversee funding and development of various nuclear fission projects. Less than a month later, Germany invaded Poland, giving the letter and the information it contained a new urgency. The committee gave money to the Columbia team for additional pile research, and Fermi was able to spend the next 18 months building a larger pile on the 7th floor of the physics building. As more material was added to the project, eventually reaching 6 tons of uranium oxide and 30 tons of graphite, the pile was moved to Columbia's Schermerhorn Hall. When the United States entered the war after the December 7th attack on Pearl Harbor and the declaration of war by Nazi Germany, the S-1 Committee met again to reevaluate the projects it was funding and to make some decisions about what directions to take in research and production. As we will cover the physics of developing a nuclear reactor and an atomic weapon in the next podcast episode, let me just briefly describe the options available. One way to make all of this happen is to enrich the uranium ore you have on hand. The idea is to increase the percentage of fissionable U-235 until you have enough that the number of captured neutrons leads to an increase in fission events so that you have a self-sustaining chain reaction. If this is done in a controlled way, you have a reactor that's able to produce energy. If you allow it to happen in an uncontrolled way and the chain reaction proceeds rapidly enough, you have a bomb. The other way to do this is to use a synthetic element that had been actually discovered at the University of California, Berkeley by Ernest O. Lawrence and Glenn Seaberg using the cyclotron there. It turns out that if U-238 absorbs the neutron in the right way and then undergoes beta decay, you can produce an element 93 and then another element 94, and that element is called plutonium. While this process is similar to what Fermi had thought was happening in his 1934 experiments, Lawrence and Seaborg had shown that the process was somewhat different than Fermi had suggested. It turns out that plutonium has the same neutron absorption properties as U-235, including the tendency to undergo fission after picking up a neutron, and, in that reaction, giving off multiple other neutrons. The advantage of this is that it's easier to separate chemically from the other things in which it's embedded. Moreover, it turned out that if you set up a nuclear pile, the uranium-238 atoms that did absorb neutrons would often be converted into plutonium, which again could be easily separated using a chemical process. The committee, headed at this time by Nobel Prize winner Arthur Compton, decided that the pile research was vital to both understanding whether a self-sustaining reaction could be achieved and to produce plutonium. In late 1941 and early 1942, Compton established the Metallurgical Laboratory at the University of Chicago and enlisted the research team from Columbia to develop a self-sustaining reactor using the Columbia pile models. Over the course of the year, Fermi traveled to the University of Chicago to work with Compton's team to develop that pile. First slated to be built in the Argonne Forest outside of Chicago, a labor dispute brought the project onto campus, where the materials were assembled in an unused squash court under the bleachers of Stagg Stadium on the campus. In this design, the graphite blocks were machined to have 3 impressions in which were placed uranium oxide eggs. That's what the shape of these things looked like. So think of like an egg carton, but it was out of a solid block with 3 sort of holes that you could put your uranium oxide eggs in, and you could put a top on top of that. Fermi calculated the needed size and shape of the pile and oversaw its general construction. Into the pile were built control rods that would absorb neutrons to keep the reaction subcritical. One of these rods could be removed in a controlled fashion in order to allow the number of neutrons interacting with the uranium to increase. If the rod was removed far enough, it was thought that the pile would quote-unquote go critical, with the number of neutrons being emitted continuously increasing. On December 2nd, with the pile not quite finished, Fermi determined by calculation that the baseline neutron activity level was sufficient to try a test to see if the criticality could be achieved. Physicist George Weil removed the control rods step by step, a small amount each time, while Fermi recorded the neutron activity level and calculated to see how things were progressing. During this run, there was a safety rod held in place above the pile by a rope that was to be released if one of Wood's Geiger counters indicated that the reaction was too intense. Additionally, there was a person stationed near the rope with an axe to cut that rope in case the Geiger counter trigger failed. As a final safety precaution, 3 students were given buckets of cadmium sulfate, a material that would highly moderate the reaction, and told that if the pile began to melt down, to run in and throw the buckets of calcium sulfate on it. On the first attempt, as Weil pulled his control rod out, the neutron level did spike enough that the emergency control rod was triggered and crashed down its tube through the pile, just as it was designed to do. Fermi, satisfied that everything was going according to his calculations, called for a lunch break. After lunch, the emergency control rod was reset, as was the threshold level for it to be triggered, and the experiment resumed. Weil withdrew his control rod up to the point he had before, and then a bit further. At the point just before Fermi calculated the pile would go critical, he had Weil stop and fully reinsert his rod. The emergency rod was also inserted fully. Now, with all the instruments recording, Fermi had Weil remove that control rod that he was holding 12 inches past the point he had previously. Then the emergency control rod was fully withdrawn and the growth rate of the neutron production was recorded. As I said at the intro, at 3:25 p.m., Fermi, watching the plotting pen on the tracking chart, declared, quote, "The reaction is self-sustaining," unquote. He allowed the intensity level to continue to grow for another 11 minutes until he gave the instruction to reinsert and lock down all of the control rods. Compton, when hearing of the result, telephoned the head of the S1 committee, James Conant, with a coded message. Here's what they said to each other. From Compton: "The Italian navigator has just landed in the New World. The Earth was not as large as he had estimated, and he arrived at the New World sooner than he expected." Conant replied, "How are the natives?" To which Compton said, "Very friendly." Shortly after this, the committee was absorbed into a larger military effort now known as the Manhattan Project. Prior to the war, the various research being conducted was subject to a great deal of review and oversight, and thus moved along at a slower pace. While the S-1 committee had accelerated the pace of research after the U.S. entry into the conflict following the bombing of Pearl Harbor, progress was still slower than the British team researching similar issues would have liked. By 1943, the overall work of the S-1 committee, as well as the British efforts, were brought together under the auspices of the U.S. Army under the command of General Leslie Graves. Once Graves took over the administration of the project, he followed a process of pursuing a large number of paths of research with less oversight. Graves was willing to accept a certain number of mistakes and dead ends if it meant that the technology could be produced more quickly. Additionally, as the project picked up steam and began to show results, more and more resources were made available to achieve its ends, eventually reaching something around 2.5% of the Allies' total war expenditures. Over the next 18 months, Fermi would oversee the moving of the CP1 pile to the Argonne Forest site, originally planned for continued research with more materials, and it was rechristened as CP2. This would lead to the construction of the X-10 pile at the Oak Ridge National Laboratory site in Oak Ridge, Tennessee, and the plutonium production reactors in Hanford, Washington in September 1944. Fermi's team's work at Hanford was vital to the success of the project, as they were able to overcome a substantial difficulty caused by radioactive decay byproducts. Once the Hanford reactors were online and running, Fermi joined the Manhattan Project's main scientific team in Los Alamos, New Mexico. Persuaded to join the effort by Robert Oppenheimer in mid-1944, Fermi was made associate director of the lab and director of the F Division, which was responsible for most of the theoretical work being done on the Mesa. On July 16, 1945, the Trinity weapon was tested, and Fermi was on hand. As part of the test, he estimated the yield of the bomb by dropping various pieces of paper and seeing how far they were moved back by the shock wave. His estimate was that the bomb's release was equivalent to around 10 kilotons of TNT. More precise estimates, calculated from more detailed observations, arrived at a number of 18.6 kilotons, within a factor of 2 of Fermi's crude method. In his role as associate director, Fermi served on the Scientific Advisory Committee for Target Selection and learned of the successful use of each weapon, like all those working at Los Alamos, through the public address system. Unlike many of the scientists, however, he didn't feel that the atomic weapon would deter further warfare or that it would, as H.G. Wells had predicted, lead to a world government. History has shown that for the most part, nuclear weapons have been largely responsible for the cessation of direct global power conflicts. However, while the United Nations was a result of the events of the Second World War, especially at its conclusion, it is far short of what many futurists expected, validating Fermi's skepticism on that account. Following the conclusion of hostilities, Fermi transitioned with the Manhattan Project to the Atomic Energy Commission and headed up the first national laboratory at Argonne Forest, the former site of the Metallurgical Laboratory. While directing the lab, he continued to work at the University of Chicago, supervising students. During this time, he continued his work with Leona Woods, now known as Leona Marshall, as she had married another physicist that had been a part of Fermi's team, and they worked together on neutron scattering experiments. Additionally, he contributed to the theoretical work of Maria Mayer on something known as spin-orbit coupling in her work on nuclear shell modeling. As you will recall from the Into the Nucleus episode, the nuclear shell model was one of the theoretical attempts to model the structure of the nucleus of the atom, given the data that X-rays and gamma rays emitted from the nucleus during various nuclear processes showed discrete spectra indicating quantized energy levels. Fermi suggested that the certain regularities found in the observations of different nuclei might arise from the spin of the protons and neutrons interacting with other quantized nuclear properties, such as the so-called orbital quantum number for each of the particles. Mayer followed up on this suggestion and found it to be very helpful in explaining a great deal of the observational evidence from a theoretical perspective. Mayer would receive the 1963 Nobel Prize in Physics for this work, becoming only the second woman to do so. Later, in his role as a member of the physics faculty at Chicago, Fermi did important work in particle physics, being among the first to suggest that certain types of subatomic particles known as pions might actually be composite particles consisting of even smaller, but as of then, undiscovered particles. This insight would be later vindicated by the discovery of quarks, though the path to that revelation would be through renormalization theory and the work of Murray-Gell-Mann. Perhaps Fermi's best-known piece of post-war scientific thinking, at least in the popular mind, is that of the Fermi paradox. While this topic is best left for a standalone episode, as it leads to a great deal of thinking and scientific hand-wringing, let me briefly sketch out the story surrounding it. In 1950, while doing some work at Los Alamos, Fermi sat down for lunch with several colleagues. The group were discussing a number of recent UFO reports and joking about the presence of extraterrestrials as an explanation for the disappearance of a number of trash cans around town. After a few minutes of this, the topic of conversation turned to other things, as is often the case in such discussions, until Fermi abruptly blurted out, "Where are they?" or "Where is everybody?" At this, general laughter burst out around the table, as while the topic of conversation had changed, everyone knew instinctively what Fermi was talking about. At this point, there is some divergence in the account of the story. In some tellings, it ends with Fermi's outburst, while in others, it ends with something of an animated discussion about trying to do a back-of-the-envelope calculation of the number of spacefaring civilizations in the Milky Way galaxy. In either case, the paradox Fermi is pointing out is that due to the vast number of stars in the galaxy, it seems very unlikely that we would be the only civilization to have, at this point, reached intelligence and communication. And yet, there are almost no scientists who believe that contact has been made with extraterrestrial civilizations, in seeming contradiction to the high odds of them existing. For those familiar with this subject, you know that an entire cottage industry has grown up around this paradox and the attempts to find an answer to it. Beyond these attempts, there's also a healthy debate as to whether such SETI, or search for extraterrestrial intelligence exercises, constitutes actual science, or if those efforts fall within the realm of pseudoscience. We'll leave such questions to a later date. In his role as the director of the Argonne National Laboratory, Fermi stayed involved in U.S. nuclear energy policy and weapons development. When, in 1949, the Soviet Union detonated its first atomic weapon, there was a serious push among many of the members of the former Manhattan Project, now involved with the Atomic Energy Commission, or AEC, to develop a more powerful weapon based on the fusion of hydrogen atoms, a process that would release more binding energy per nucleon than the fission of plutonium atoms would, thus producing a much greater yield for the weapon. Fermi opposed the development of this so-called hydrogen bomb, but when the AEC decided to move forward with the research to develop the technology, Fermi did calculational work on various aspects of the project. Prior to his death in 1954 of stomach cancer, one of Fermi's last acts was to testify on behalf of Robert Oppenheimer during the latter's hearing as a security risk during a period of anti-communist hysteria in the United States. Following his passing, Fermi was memorialized in many ways and by his many collaborators. C.P. Snow, the preeminent 20th century historian of physics, wrote, quote, "If Fermi had been born a few years earlier, one can well imagine him discovering Rutherford's atomic nucleus and then developing Bohr's theory of the hydrogen atom. If this sounds like hyperbole, anything about Fermi is likely to sound like hyperbole." Victor Weisskopf said Fermi, quote, "always managed to find the simplest and most direct approach, with the minimum of complication and sophistication," unquote. In closing this episode of the podcast, I think it appropriate to leave the last words to the subject himself. Fermi, in spite of his generally hopeful and optimistic nature, was deeply skeptical that humanity could manage the technology it had created wisely. In an essay titled The Future of Nuclear Physics, written just 2 years prior to his death, Fermi wrote, quote, "Some of you may ask, what is the good of working so hard merely to collect a few facts, which will bring no pleasure except to a few long-haired professors who love to collect such things and will be of no use to anybody because only a few specialists at best will be able to understand them? In answer to such questions, I may venture a fairly safe prediction. History of science and technology has consistently taught us that scientific advances in basic understanding have sooner or later led to technical and industrial applications that have revolutionized our way of life. It seems to me improbable that this effort to get at the structure of matter should be an exception to this rule. What is less certain, and what we all fervently hope, is that man will soon grow sufficiently adult to make good use of the powers that he acquires over nature." Unquote. Excellent words for us all to ponder. Until next time, full sails on your journey.